However, back in America, another company is setting out to prove for the first time that a pod can be propelled along a full-scale track at high speed, and that it's safe for passengers. In January 2017, their team were assembling the world's longest full-width Hyperloop tube at 1,600 feet. Still not long enough to accelerate up to aircraft speeds, but potentially enough to surpass high-speed rail.
The nice thing about doing something that nobody has ever done before is that nobody can tell you how to do it. However, that's also a curse, is that nobody can tell you how to do it. So we learned, we tried different things. We made plenty of mistakes, but we also learned how to do things quite a bit faster. Like at the beginning, we could only install maybe 1 or 2 feet of track per day. By the end, we were installing 30, 40, 50 feet of track per day, and that was all because we were learning about the process.
Josh Geigel is co-founder of Virgin Hyperloop. Having previously worked at SpaceX, Josh read the Hyperloop paper by Elon Musk in 2013.
My initial read was like, this feels like a little bit of a crazy idea, and there were some mathematical errors in it that I jabbed my friends about. And shortly after that, I decided to look at that with a future colleague. And the idea of tackling a new idea in transportation really became powerful. The ability to build something that nobody had ever conceived of before. Like everybody knows a car has 4 wheels, an airplane has wings, but what does a Hyperloop have? A Hyperloop could have anything we imagine. So we started out in a garage in North Los Angeles in November of 2014. And the goal at that time was how quickly could we build a prototype, a piece of technology to show that this idea was even feasible. And that's what we really set out to do, is like, let's figure out what we can build to demonstrate that a Hyperloop is even possible. We looked at a lot of different places for a test track, and Las Vegas is pretty close to Los Angeles, and we picked the desert. It would get down to about 0 or -5 Fahrenheit in the winter, which was pretty cold. And then in the summer, it'd be about 120, 130 degrees Fahrenheit.
The extreme swings in temperature would cause the steel track to expand and contract by over a foot. So the tube could only be fixed in one place. Along its length, the team installed rings to allow for expansion. And by elevating the tube above the ground, the Hyperloop track should have less impact on wildlife and the environment than a conventional rail line. By March 2017, despite the challenging weather, the team were building the test site at a phenomenal rate.
Today, they're actually started commissioning the vacuum tent for the first time this week. And this is where we actually create the low pressure environment inside the tube. So this big setup you see is our actual vacuum system. So we have a number of blowers, pumps here at the top, and they come in, they suck through these 8 pumps, they come through these 2, and they eventually go through these 4.
The pumps reduce the air pressure in the tube to the equivalent of 200,000 feet of altitude, almost 6 times the cruising height of airliners.
So if you can see right now, they're actually installing the control system for this particular pump. And this is the first time they're actually doing this, so it's a pretty exciting day today.
Reducing air resistance is a key step towards achieving high speeds. But another critical factor is the propulsion system itself that will be fitted inside the tube.
So these are part of our motor system. These are copper coils that we had the design to actually create the propulsion wave that the vehicle would follow down. So when we built our facility, we needed about 3,000 of these individual coils.
The coils will be lined up along the middle of the track, where they can interact with magnets on the pod. Adjusting the flow of electricity through the coils creates different magnetic fields. Those in front pull the pod towards it, while those behind push it away. This pattern continues along the track, speeding up as the pod gets faster.
You basically send this electrical wave down the tube just like a surfer riding a wave. A surfer likes to stay at the top of the wave so that he gets the propulsion. So you're trying to synchronize those two fields, get up to whatever speed you're trying to go.
Alongside all the track components, yet another team are hard at work on the capsule to travel inside it, including structural engineering manager Helen Durden. First, they're building a sled, which will eventually form the chassis of the capsule. But building a vehicle that's so new and untested poses a unique challenge.
What's been interesting is we start not knowing very much what it's going to wind up being. Like every other job I've had, it was spacecraft, aircraft. You have a lot of very well documented, solid standards. For this one, we went through all of it and got to pull what we think fits best, because this is somewhere between a car and a train and a plane. And maybe not a spacecraft, but NASA has really good open source docs, so we like to pull from those too. So that's a very unique thing with this, is really starting from scratch.
Once ready, the sled will be used to test the whole system for the first time.
There's always something pretty magical about seeing this design that it's always on my computer screen every day. Actually seeing it now here in aluminum and steel and welds and bolts, there's something, like for me, that's still a rush.
By May 2017, just 12 months after starting construction, enough of the track and sled were ready to test the overall Hyperloop. The individual components had all been shown to work on their own, but this would be the first time everything came together.
So it'd be one thing to build all of these individual pieces of technology in the lab. It's something completely different when you bring it all together and have to integrate the system. That level of risk with system integration, with the complexity that exists there, is really big.
Tube confirmed ready for test. Fire VFD and announcement test complete. Fire in 5, 4, 3, 2, 1, fire.
The whole vehicle lifted off. It was on magnetic levitation. It was using our propulsion system. That first test didn't go very far. It went about 10, 15 meters or so, or about 30 feet. But to be there with the group who put their blood, sweat, and tears and actually making this happen and see the elation on their face was something I'm never, ever, ever, ever going to forget.
They'd proved that the technology works, albeit at a leisurely 70 miles per hour. Next, they needed to push the system to its limits and demonstrate that Hyperloop really could be the fastest way to travel over ground.
3, 2, 1, fire.
The goals of the test after that were to go further and faster. There was a Saturday in July of 2017 where one of the most exciting days, if not the most exciting day of testing I ever had, we were just going faster and faster about every 2 hours. We would run a new test, a new test, a new test, and every test would go about 20 miles an hour faster.
The first time we got up to speed, I was just curled up in fetal position on a chair, like so terrified, but then it worked. It was pretty awesome.
Top speed we ultimately got up to was about 240 miles an hour, about 387 kilometers per hour, which is faster than the normal speed of high-speed rail. So we were able to do that very successfully, very quickly, and show that this could work.
The team had shown that Hyperloop could be faster than high-speed rail, even with only a third of a mile to get up to speed. Next, they needed to show it was safe for passengers. First, they had to build the shell of an actual capsule on top of the metal chassis. This prototype pod would never carry passengers itself, but would take the team one step closer to that milestone.
We put this big shell on the outside, and that completely changed the characteristics of the vehicle. And so once we did this, we had to relearn how to control the vehicle. So with that vehicle, we got up to speed. We learned about the aerodynamics, even though there's not a lot of air in the tube, to ensure that this could actually work.
With the system now finely tuned, the engineers could start work on the passenger-carrying pod itself. The main challenge was to design a pressurized capsule that could withstand a vacuum equivalent to being near the edge of space.
The next one actually needed to be a vessel safe for humans. So we started from scratch, built basically from the ground up a vehicle that could essentially fly at 200,000 feet of altitude. I mean, we built a spaceship. Over the course of about a year and a half, we got it certified. We got it independently assessed to be safe so that myself and one of my colleagues, Sarah, could ride in it.
By November 2020, the capsule was ready for the world's first passenger Hyperloop ride.
I knew I had to be the first one. Starting this company, if it wasn't going to be safe enough for me, it wasn't going to be safe enough for anybody. It was way more excitement than nervous. And the excitement was to be sitting in essentially an idea. And there we were sitting in a Hyperloop that was kind of concepted on a whiteboard that you'd seen through ups and downs, you had nurtured, you had grown, you'd cried over, you'd done everything over. And here you were in the moment of like the most monumentous day in the history of the company, showing that it could work.
3, 2, 1, launch.
Yes. You feel this force, this acceleration. In this case, it's a little bit harder than normal, but it would be about like a performance sports car. It's about 0.6, 0.7 Gs or so, pushes you back into your seat. System gets up on the levitation. It was smooth. It was kind of unlike anything that I'd ever experienced before.
That was so good.
That was awesome. Oh my, that was awesome. The pride, the understanding of just how hard it was to get here was something that was humbling, to say the least, to be able to even ride in something that you've created in a new mode of transportation with everybody watching and safe, and it was surreal.
But despite reaching this huge milestone, Josh now faced a setback. The next step would be to build an even longer track capable of reaching true Hyperloop speeds. But when they ran the calculations, it became clear that the technology used in Nevada would not be economical over greater distances.
In the same way, you know, Edison discovered 5,000 ways not to make a light bulb, we discovered a lot of things that we shouldn't make a Hyperloop like this. And so we had to reconstitute, re-architect our system to ensure that we could get to a price point that would allow us to deploy systems all over the world.
Building and maintaining the infrastructure to power the propulsion along hundreds of miles of tube would be too costly. One estimate for a Californian Hyperloop suggested the price could reach over $100 million per mile. And as technology inevitably improves, it would be a huge job to upgrade the entire network.